Hello students, in these slides we'll cover a new concept and very important topics in data structures and algorithms. It calls algorithm complexity analysis. We'll see how to calculate complexity of an algorithm. So what is algorithm? Algorithm is a set of steps of a program. So when you are going to write a programs, before writing a programs, you probably design that what are the steps you should have in your program. So you write your steps, and after writing a steps, then you can follow some technique which which basically try to find out the complexity of the of your algorithm. That means you try to find out how complex of your program would be. So how many time it will need, how many space it will need, so you can calculate those things at the design level. So when you are designing your program by writing different steps, so you must have idea idea how to analyze the complexity of the programs. So what is the motivations to do that? So there are basically tools to measure low how fast a program runs, such as profilers. So profilers some kind of tools that tell you that how fast your programs. However, what we are talking now is not something like that. It's something that you want to know that whether your program would be uh, uh, how, how you just want to measure your future program. That means you are at the designing level and you didn't implement your program yet, but be at the design level you want to understand that your program how fast your program would be. So that's a good idea because if you spend a lot of time implementing a program, and after implementations of your program you understand that your program is not efficient and it's taking longer time, so what you need to do, probably you need to design again and you need to implement again. So this is kind of is you know wasting your time, wasting your money and a lot of things. So that's why the good idea is that before jumping to the implementations, you you should calculate your future programs at the design level. So we'll discuss about different techniques how to compute complexity of a programs at the design level. So this is the algorithm or programs that perform just a computations. Complexity analysis is also a tool allow us to explain how an algorithm behave as the input grows larger. So it also tell you so these analysts also tell you, for examples, uh, if your program taking some user input, so and you don't have idea how large your user input would be, then it's a good idea at design level you measure that. If you have a very large user input, then how your program behave. So how your program behave. So when you try to find out this kind of measurement, we always think about that probably we will have very large user input. So we always think about very large user input. For example, so you wrote a you are going to write a program that might takes some user input. So you should think that a user input could be billions of data. So if your program takes billions of data, then how your program will behave. So you have to understand, you have to analyze this situation at the design level. So if you think that your program is not you know doesn't have any impact, even user input grows larger, so then your program is good programs. But if your program has very bad impact, when input grows larger, then this program is need to be improved. So these sort of things we should we should do at the design level. So before calculating complexity of an algorithm, so the basic thing is that counting instructions. So what is counting instructions? We know that a program has set of statements, and the statements are you know uh, statements contains several instructions. So what are the instructions? There are five different basic instructions. So these different basic instructions are used to create several statements and programs. So what are the basic instructions? Assigning a value to a variables. We are assigning something to a variables. So this is one basic instructions. Looking up the value of a particular element in an array. So we are looking uh, for a particular value at specified index. Compare two values, increment or decrement values, some basic arithmetic operations such as addition, multiplications. These are the basic instructions in our programs. So now uh, here we have a small program. So if I ask you that how many instructions that each statement has. So for example, if you go to first statement, the first statement, try to find out how many instructions over there. So this is one instructions. The first instruction basically looking for a value at zero index. So this is one instruction. You can see the looking up the value of a particular element in an array. So we are looking a value at zero index. This is one instruction. After finding that value, we are assigning to a m. So this is another instruction. So this statement basically has two instructions. So what are the two instructions? One instruction finding value at zero index, and another instruction is assigning that value at you know uh, variable m. Now go to the next instructions. So in the for loop, this is a for loop. So if you understand for loop, so the for loop runs several times. So this for loop runs n times. So here we can see that I less than n. That means I started with a 0 and I less than n and I plus plus. That basically saying that this for loop runs I time. So we know that for loop runs I times, but this assignment doesn't happen I n times. So this doesn't happen n times. A for loop runs n time, but these assignment doesn't don't happen. This no this assignment don't happen uh, n times. It's only happen one time. So before starting a for loop run. So for loop statement. So when you have the I equal to 0, then this comparison happen n plus 1 time. Why n plus 1 time? Because it runs n time, and last time it will not run for loop, because last time it will not satisfy the conditions and it will not run these statements inside the for loop. So this I less than in the comparison expressions, this comparison instruction will happen n plus 1 time. And how many times I plus plus I happen? The plus plus I happen n times. So this also happen n times. So now everything inside for loop, probably in worst case probably it will happen n times. So if it is satisfied, then it will come to the if conditions, and the if conditions, they have some comparisons. If you consider these comparisons, a I a of I, that means it's looking for some value at I index, and so this is one instructions. After finding that value, you it compare with the m value. So this is another instructions. So there are two different instruction, content in this conditional expression contains two different instructions. Now if you go to this instruction, this is this one is the one instructions. it looking for some value at I index, then after finding that value it assigned to the am am variables. So these statement has two instructions, this conditional expression has two instructions, and this one is a one instruction, this one is a one instruction, and this one is a one instruction. But this runs n times, this run n times, and these all two runs n times, and these all two runs n times. Probably it's not exactly in time, but you always think the worst case. In worst case probably it will run in times. So now if you calculate the total number of instructions, these are the two. We can see that there are two instructions over here. This is one instruction and run one time, this is one instruction run in time, this is one instruction run in times, and here two instruction and two instruction, four instruction, all four instructions run on n times. So 1 2 3 4 5 6, these six all instructions run n times. However, here these two, these now this one three, and here we have talked about n plus one, that so extra one instructions. These four instruction doesn't depend on n value, so probably we have total number of instructions 6 and plus 4. So let's see, so 6 and plus 4 instructions. We often consider worst case scenario when analyzing algorithm that we have discussed. Probably the if condition inside the program will not run in times, but we will always think about worst case scenario when we analyzing algorithm. So algorithm needs more instruction to complete. So probably it might needs more instruction to complete. So the total instruction is 6 and plus 4 that we have discussed. So what is the best case of your example? So best case probably have smaller number of instructions. For examples, it it doesn't satisfy, it never satisfy this one. So probably that would be the best instruction. Uh, Best cases, in best cases you need less number of instructions. So this is worst case analysis. We are analyze the worst case of the program, so it always runs all the instructions all the time, so we can find the how many instructions we need to complete, perform this program. So so if you understand how many instruction you need to perform, the program needs to perform, then probably you can understand that how complex your program, how long it will take. So now let's talk about the asymptotic behavior. Asymptotic behavior is something, say if you, we always care about some input which is grows large. For examples, if you consider this one 6 and plus 4, 6 and plus 4, that coming from the previous slide, 6 and plus 4. Now if n grows larger, say for example if you have n equal to 1, then your total instruction is 6 into 1 equal to 6 plus 4, total 10 instructions. If your n equal to 2, then 6 into 2 equal to 12 and plus 4 equal to 16, you have 16 instructions. If you n equal to 3, then you have 6 into 3 is 18 plus 4 equal to 22 instruction. That means you always have 6 and 4 are constant, but your n is grow larger. So that means how your program behave, that basically depends on n. So that depends on n. If you have larger n, then probably it needs more time. If you have lower value for n, then you might need lower time. So why don't you keep only n and you just remove 6 and 4, because these are the constant, you don't need to worry about that things. So asymptotic behavior is something you remove all the lower values, lower components or constant component that basically doesn't affect your programs. You only keep that larger value basically largest value, that basically killing your program. So we'll keep only n and we'll remove 6 and 4. So if you remove 6 and 4, then probably you will have fn equal to n, and that dropping all factors, keeping the largest growing term is called asymptotic behavior. So you keep only the largest growing term. Here is the largest growing term is n. So n basically grow largest way than other two components, 6 and 4. That's why you will keep only n and you will remove all other two. So dropping all factors and keeping the largest growing term is called asymptotic behavior. So this is a asymptotic behavior. Now let's see some examples. You have, say for example, you have 5n plus 12. So that basically 5 is a constant, 12 is a constant, you keep only n. Now if you have 109, that doesn't have any variable, something like n, so this is basically 1. If you don't have, if you have only constant, then that basically saying that it's a 1. Now in that case you have n squared plus 3n plus 112. So you remove 112 and you keep only n squared, because n squared is larger than n. So when n squared is larger than n, so you just keep the largest thing. So you keep n squared, you remove 3 and 112 because these are the lower. So now if you consider this one, you have n cube plus 1999 n and 1337. So you remove all three, but yeah, you remove all other, only keep n cube because n cube is the largest one. So asymptotic behavior is keeping only the largest growing element and remove all other things. Now come to the complexity. So how do you count your complexity? So the best way to count your complexity by counting the loops. So you might have for loop, you might have while loop, you might have some recursion that will cover. So that basically, by counting a loop you can find out the complexity. So if you have a single loop over n element, n item, then you can say the complexity of the program is n. If you have a loop within a loop, that means you have a loop within a loop, then you can call that is n squared. If you have a loop within a loop within a loop, then probably you can have n cube. So these are the loop. So if you have loop inside another loop and inside another loop, then probably you'll have n cube, something like that. So counting loops is the way to counting complexity. Let's go to some examples. So before going to examples, this is one important information. Given a series of loops that are sequential, the slowest of the determine the asymptotic behavior of the programs. Say for examples, if you go to the terminals, say you have some programs. Say for example, you have a programs. The first one is run n times, and second one, say you have this for loop, and second for loop run, say for example, int I less than, say n into n I plus plus. This is your second loop. So you can see that there are two for loop, but it's not inside another loop. So this for loop not inside this for loop. This is sequential. So one is followed by another one. So now you can see that this for loop run n times and this for loop run n square time. So we know that n square is largest one, grows slowly and it's the largest value, and this one is a slower element. This is a slower element and it runs faster than this one. So probably if you think it runs 5 minutes, uh, probably it will need more, some more minutes, more than 5 minutes, because it's an n squared. So we'll consider only these things. So if you want to count the complexity of these two of these programs, so you will think about the n square only, because this one is the largest one. You just ignore this one because it is smaller one. Now if you take this one, if you take this one and you keep inside these things, then you have n square over here, and inside that you have n. That basically create n cube. N square into n, that basically n cube. The complexity of this program is n cube, because one for loop inside another for loop. The first for loop is n square. The inside for loop, the inner for loop is n. That basically create n cube. We'll see some example also in slides. So when you have sequential for loop that we have seen on the terminal, then we'll only think about the slowest for loop, which has largest element. So now try to find out the complexity of the program. So if you analyze this program, you can see that this is one for loop, and inside that for loop you have another for loop. So we can we can understand that probably this program has n square complexity. This is for one n, this is for another n. So n square. So n into n square. The program have n square complexity. Now, if you consider these programs, you can see that this has one for loop and it runs n time. So this for loop, this program has n complexity, big O n complexity. Now, if you consider these programs, this program has one for loop and this program runs n time, but it also calls f of n functions, but we don't know what is the complexity of f of n function, because f of n function is not defined over here. So we don't know what is the complexity of the program. Is undefined, because f of n, no, f of n is not defined over here. We don't know the complexity of f of n, so we don't know the complexity of the whole programs. Now if you consider these programs, these functions has one for loop, and this for loop run k times, and then you can call that this is a k complexity. Now if you come these programs, this program has this for loop and it runs n plus 100. If you remove 100, because we only care about the larger element, so we say that this for loop runs n time, and inside that they have two for loops. This for loop runs I into n times, and this for loop run 3n time. So 3n time means n time, because we remove 3, so we have 3, this for loop run n time, because 3n equal to n, so we remove all the constant, so that's why it's for loop run n time. Now if you consider this one I into n, what is I basically is n. So that basically I is, so since I coming from these for loops, so I basically n. So this basically means I into n means n into n. So n into n means n square, and the outer loop has n. So this the whole program complexity is n cube. These for loop run n square, this for loop run n time. So we only consider this for loop because this is the slowest one. It has larger element among these two for loop, so we'll only consider this one. Now outside for loop has n time, and this for loop has n square, so in total this program needs n cube complexity. Now if you consider this one, these for loop run n times and they have some if conditions, so the complexity of the program is n complexity. Now think about this one. Say you have for loop over here n times, and it increment j plus 2, so that doesn't make sense. So j plus 1 and j plus 2 is almost similar. So now you have a for loop over here that runs j times, and you have another for loop over here that runs n times. So this one is a n times, this one is a j times, and this one is a n times. So if it is n times, so what is j over here? J basically is another n. So because j is coming from here and j j runs in time, so j basically n. So this is running in time, this is running in time, and this is running in time. So the whole complexity of the program is n cube, because all the for loop are inside another. So another for loop, so you have for loop, inside that you have this for loop, inside that you have this for loop. So that basically create a n cube. Now big O notations. Big O notation is something we always consider, worst case of our program when we try to analyze our programs or our algorithm. So for example, it's sometimes is very difficult to find out exact complexity of a program, but it would be easier if you try to find out that your programs would not be slower than that time. It would not be worse than that things. So when you try to express your complexity in that manner, then that basically you should represent your complexity using big O notations. So big O notation is saying that our program is not worse than that. So but we don't know exact complexity. So when you don't know the exact complexity and you want to represent that your program is not worse than that, then you have to represent in a big O notations. So sometimes it's hard to figure out exactly the behavior of the exact behavior of the algorithms. So we are able to say that behavior of our algorithm will never exceed certain bound. So it will never access certain bound on it's not worse than that time you can represent your complexity results using big O notations. So if you consider this one, so in this there is a loop. This is some Ruby code. So this is a loop n dot times, this is a loop while like a while loop, and this is a like a for loop. So there are two for loops. The problem is that every time you know uh, every time this loop basically remove some element, the outer loop before running second time it remove the one element. So when it remove one element, so second time it will not run n times, it basically run n minus 1 time, and third time it will run n minus 2 time, fourth time it will run n minus 3 time. That basically saying that all the time is not run n time the last for loop. So you cannot say this program will run n into n square times, because it's not exact solutions. But you can say that your programs, this program will not never run, will never run more than n square time. And in that case you should represent that n square using big O notations. So big O notation will represent in that way. So big O n square. So we basically say the upper bound, we find some upper bound, our program will never exceed this time, this is the upper bound, and this upper bound is presented by big O notations. So the upper bound of this example is something like that, big O notations n square. So n square is our complexity, and the big O notation saying that this is not an exact solution, but our program will never exceed n square time. So it is easier to figure out big O complexity of the algorithm than its theta complexity. Theta complexity is something that basically the exact complexity. So it's always hard to find out exact complexity. So that's how we care about the big O complexity. So, but a program that is big O n square may not be the theta n square, because big O n square basically upper bound and theta n square is not upper bound, is a exact solutions. So we can say that a program that has a big O n square may not be a theta n square, may not be the exact solution that we are talking about. So similarly, we can do some, a theta n algorithm is big O n. So if you consider a program is theta n, that you can represent that as a big O n also. So if you are able to find exact solution, you can exact complexity of your program, then you can represent that as a big O n square also. If you find theta n, you can also represent as a theta n square also, because this is also a upper bound and of that. If you find theta n square, you can represent that a big O n cube also. This is upper bound of this program. But if you have theta n, you cannot tell them big O 1 because big O 1 is not, large slower than this one. This is faster than this one, and so this cannot be upper bound. So this is a wrong thing. So theta n should cannot be, it cannot be represented as a big O n. So these are the basic thing of the algorithm complexity. You should read these, chapters to understand properly. You will have a lot of exercise, lot of examples in your exams, whether it is midterm 1, midterm 2, or finals. You will always have the algorithm complexity problem, and most of the time students get confused to understand algorithm complexity, and they do a lot of mistakes in those programs. So you should care about those things. You should read this you should read this chapter, and you should try to read a lot of research to understand those things. Let's go to the next slide. Thank you.